In this lecture video, we will learn how to determine whether a substitution reaction or an elimination reaction will predominate. Now, we have seen already that substitution reaction and elimination reaction are almost always in competition with each other. And sometimes one reaction or mechanism will predominate versus all the time a mixture of two different reactions will occur and therefore giving rise to a very messy mixture of different products in a chemical reaction. So to be able to predict which mechanism will predominate, we have to analyze this following factor. First, the reagent, and second, the substrate, and third, the reaction condition. Each of these factors right here can help us determine whether a reactions will be favored by the substitution reaction or the elimination reaction. So now, let's discuss the first factor first, the reagent. When we have our substrate, if we were to take our substrate and react in it with a basic reagent, we would then be favoring elimination reaction. For an example, if we were to take this substrate right here and now react in this with a basic reagent, a basic reagent is basically when the reagent is behaving as a base. So it is either a strong or a weak base, but it has base characteristic to it. Then we be favoring elimination. If that is the case, in which the mechanism will proceed as follows. The base acting as the base come in, pick up one of the hydrogen at the beta location. So it will either be the hydrogen on this beta position or the hydrogen on the other beta location. This is why we also call this beta elimination as well. The electron is then donated in and kick off the leaving group. So therefore, on the product, what will be making would then be an alkene, where the double bond is now formed between the alpha and the beta location. And we will also have our leaving group taken off with the electron, and now the base will then have the hydrogen to it. So again, if we were to be taking our substrate and reacting this with a basic reagent, we will be favoring elimination reaction. Whereas if we were to now take the same substrate, but now reacting this with a different types of reagent, in which now the reagent is a nucleophilic reagent. So if we were to take this and reacting this with a nucleophilic reagent, a nucleophilic reagent is a reagent that can behave as a nucleophile. And if that's true, then we'll be favoring substitution reaction, where the reagent will then come in and attacking this alpha carbon directly, then kick off the electron. And here in this case right here, the product that is produced is when we have the nucleophile replacing the leaving group. And now the leaving group breaks up with the electron. So that's how we can distinguish between nucleophilic attack versus basic attack, or favoring substitution reaction or the elimination reaction. So let's summarize this again. If we were to add a nucleophilic reagent, we'll be favoring substitution reaction. Whereas if we were to have the basic reagent, we'll be favoring elimination reaction. Now, let's now analyze the next factor. We have seen already that in both substitution reaction and elimination reaction, it can proceed through either an SN1 or an SN2 mechanism. And similarly with the elimination reaction, it can also proceed through an E1 or an E2 reaction mechanism. Now that we know how to distinguish between substitution elimination reaction already, let's say the reaction were to undergo a substitution reaction. How do we know if it would occur through the SN1 or the SN2 mechanism? Then the answer, to distinguish, we have to analyze the substrate. It is the types of substrate that can either favor SN1 or the SN2, in which it is as follows. If we were to have the tertiary substrate, which is quite steric and therefore difficult to attack, then we'll be favoring the SN1 reaction. Whether if we were to have the primary substrate, then we'll be favoring SN2 reaction. And if we were to have the secondary substrate, then it can occur through either SN1 and SN2. And now, if we were to be doing an elimination reaction, the structure of the substrate actually do not matter at all in elimination reaction, where all primary, secondary, and tertiary all favor E2 reaction. And now, for the next factor, the reaction condition. So this is basically the solvent or from the other condition that whether we heat or we cool the reaction. And we have seen already that if the reaction were to occur, were to undergo a substitution reaction, a product solvent would then favor SN1 versus an A product solvent would then favor SN2. So that's how the reaction condition, in this case, the choice of the solvent, can help favor either SN1 or SN2 reaction. Now, if the reaction were to undergo an elimination reaction, then the choice of the solvent actually do not have much effect on elimination at all. But we have discovered the following. Heating actually favor elimination reaction. And why this is the case is something that we will be discussing in the next chapter. And everything we have discussed on this page right here can be summarized as follows. So, if we were to have reagent in which that it behave as a nucleophile only, an example of reagent that are nucleophilic, where they would only behave as a nucleophile, would be as follows: halide, such as chloride, bromide, or iodine. And these are some of the other negatively charged species that are also good nucleophile as well. So you can see that sulfur containing substances are pretty good nucleophile. And if we were to have a good nucleophile, then we know it will undergo substitution reaction. But now whether it will undergo SN1 or SN2 is dependent on the following. Let's say the reagent is nucleophilic, and now we have a primary substrate. Then this would then very much favor the SN2 mechanism, because the substrate is less steric, therefore it's very easy for the nucleophile to come in to attack. So therefore SN2 will be the predominant reaction mechanism. If we were to have a tertiary substrate and a good nucleophile, then we'll be undergoing the SN1 reaction mechanism instead, because here in this case the tertiary substrate is difficult to attack, so therefore the nucleophile will not be able to attack directly, but the loss of the leaving group would happen first. And if we were to have a second substrate and a strong nucleophile, then we can see a mixture of both SN1 and SN2 product will be observed. If we were to now have a reagent that only serve as a base, an example of reagent that only serve as the base as follow. Hydride reagent have been found to only serve as base. And DBN and DBUs, these are basically organics reagent that are base, that are strong bases. And if we were to have a reagent that only would behave as a base, and if we were to now take this and react with this with either a primary, a secondary, or a tertiary substrate, It does not matter what types of substrate it is. It will all undergo elimination reaction. In this case, all the E2 mechanism. And the reason why is because the base is strong. Therefore, you'll be able to come in and pick up the beta hydrogen directly. And because steric is not a problem in elimination reaction. So therefore, it does not matter whether you have a tertiary substrate or not. In fact, reaction rate is actually fastest with the tertiary substrate. So all types of substrate with a strong base would favor the E2 mechanism. And now, if we were to have the other types of reagent that are both strong nucleophile and strong bases, then we will be getting a mixture of both the substitution and the elimination reaction. And for an example, let's say that most of the alkoxide or hydroxide are reagents that are both strong base and strong nucleophile. If we were to take those reagents and react them with a primary substrate, then here in this case right here, the substitution reaction would then be the major product. And the reason why is that because the primary substrate here in this case right here are not very bulky, so therefore they are very easy to attack. And this is why that the SN2 would be the major product. We'll also get the E2 as the minor product as well. And if we were to have a tertiary substrate, and now our reagent are both strong base and strong nucleophile, it would be pretty difficult for the reagent to come in and attack this tertiary substrate directly. So therefore, we'll not be able to see the SN2 reaction. But then in this case right here, the major reaction would then be the E2 products. Versus if we were to have a secondary substrate with a strong base and a strong nucleophile, it can do both in both E2 and SN2. And in this case right here, the E2 would then be the major product. And the reason why that it is better acid and base reaction, that it will happen in the elimination reaction. And we have seen already that acid and base reaction happen a whole lot faster than substitution reaction. So this is why that this would then be the major products. And now, if we were to have reagent that are weak nucleophile and weak bases, then in this case right here, it does not favor either substitution reaction or elimination reaction. And so a lot of time the reaction would be pretty slow. So if we were to have a reagent such as water or alcohol, these are weak nucleophile and weak base. And if we were to react in this with a primary substrate, so here in this case right here, it can undergo SN2 or E2, but this would not be very practical reaction because the reaction rate is very, very slow to the point where we will not see a reaction at all. And if they were to proceed, they will be pretty slow reaction. Now, if we were to have a tertiary substrate, so here in this case right here, since this is a weak base and weak nucleophile, if we were to have a tertiary substrate, that is when the reaction rate will be a little bit faster. And the reason why that it will undergo either an SN1 or the E1 mechanism, where the leaving group will break off first, followed by either the nucleophilic attack or the basic attack. So we'll be forming both of this. Now, so if we were to now heat up a little bit, heat would favor elimination products over substitution products. So that's how heating can actually favor one over the other. And if we were to have a second substrate, so here in this case, this would not be a very practical reaction to perform at all. And the reason why that all of this product right here are feasible. So we'll be forming a very a mixture of various products, which is pretty messy and not very efficient in organic reaction. Let's now try some of this practice problem right here to make sure we know how to determine whether an elimination or a substitution reaction will predominate. So here in this case, let's try A. So in A, we have this substrate here reacting with sodium chloride in DMSO. So here we have a second substrate. And now we have sodium chloride, in this case, the nucleophile would then be the chloride, and we see this will be a strong nucleophile. And we have DMSO, which is basically an A product solvent. So first, let's now decide between substitution and elimination reaction. In this case right here, we will then see the reaction will have to undergo a substitution reaction because the reagent is nucleophilic and not basic. So only substitution reaction will be seen. And now between SN1 and SN2, then which mechanism will be the predominant mechanism? And the answer, it would then be the SN2. Will be the predominant reaction mechanism. And the reason why is strong nucleophile and an A product solvent favor SN2. So here in this case, now that we know that the major product would then be the SN2 reaction, then we would then see it would proceed with the inversion in the configuration. And now the nucleophile replacing the tosyl group. And that would then be the major product. And now let's try B. So here in the case of B, we have a tertiary substrate reacting with tert butoxide. Tert butoxide is a very strong base. And because it is a strong base, it will then favor elimination reaction. So therefore, we will then now know that elimination would be the major mechanism. Now between E1 and E2, which one would it be? So we see that because the base is strong base and we have a tertiary substrate. So again, all types of substrate would favor E2. So here in this case right here, we will then see that the E2 mechanism would then be the predominant mechanism. And in this E2 right here, then we can see that this is the alpha carbon and we have this beta carbon, beta and beta carbon. So we would then observe that there are two different types of beta hydrogen. Therefore, we will be forming a mixture of different products. But to determine which one is the major product, then we have seen already that in this case right here, since this is a bulky base, it would then favor the Hoffman product or the terminal alkene. And that would then be the product of this reaction. And this is the Hoffman product. The other product that may form, in which it will be forming as a minor product, would then be the Reagent products. So here in this case, the more stable alkene would not be the major product, but would be a minor product. And this is the Reagent product. And now let's try C. So here in this case right here, we have a tertiary substrate and we have sodium hydroxide. And we know the sodium hydroxide is both a strong base and a strong nucleophile. Because the reagent is both a strong base and a strong nucleophile, we will then see that it can undergo both substitution and elimination reaction. But here in this case right here, between substitution reaction, then we would then see that it would be happening through either an E2 or an SN2. And in this case right here, because this is a tertiary substrate, it will not be favoring substitution or SN2 reaction. So therefore, the major product would then be the E2 reaction. And if we were to go back to this guideline that we have seen on the previous page, we have a strong base and a strong nucleophile. And we have a tertiary substrate. So as you can see here, that the observation is that the E2 mechanism will be the predominant mechanism. So here in this case right here, E2 would then be the major products. And now we can form, again, there will be two different types of alkene that form because there are two different types of beta hydrogen. So here in this case right here, we can form an internal alkene or the terminal alkene. And in this case right here, because this is a small base, therefore it will pick up the hydrogen on the internal carbon to produce the internal alkene, because that will be the most stable product. So the major product will then be the more substituted or the most stable alkene. And again, this is called the J-test products. And this will then be the minor product. And this is the Hoffman product. And let's now try D. So here in this case right here, we have a primary substrate and we have a good nucleophile. So guys, you can then see that it will be very much favoring the SN2 mechanism. And the products, SN2 product of this, then be as follows. And now let's try a few more one. Let's try H. So here in this case right here, what kind of reaction mechanism will be the predominant? So here in this case right here, we have sodium hydroxide, which is both a strong nucleophile and also a strong base. So therefore, both substitution and elimination reaction can occur. And now in this case right here, we have a secondary substrate. And we will then see that second substrate can undergo both the E2 or the SN2. So therefore, we can see that we will see both SN2 and E2 products being produced in this reaction. So now let's draw the SN2 product first. The SN2 product is when the hydroxide come in to attack this carbon from the back directly and kick off this bromine. So the attack happen at the alpha carbon. And the products will then be as follow. And again, this is a stereospecific reaction, and we will only be making the product where the hydroxy is pointing in the back, the opposite direction where the leaving group is. So this will then be the SN2 product. As for the E2 product here, in this case right here, we will then see that that when the reagent will then come in, acting as a base to pick up one of the beta hydrogen. So here in this case right here, we have a beta hydrogen above here, and we also have beta hydrogen, 2 beta hydrogen over here. So in this case, as if we still remember about the E2 mechanism, that in order for it to undergo E2, the hydrogen and the leaving group have to be anti-periplanar to each other. And here in this case right here, this hydrogen right here is pointed on the same direction at the leaving group. So therefore, we can see that elimination reaction will not occur where the base will then come in and pick up this hydrogen right here. Because again, this hydrogen right here is not at the anti-coplanar or the anti-periplanar approach. But now, on the other carbon, this carbon right here, this hydrogen now pointing both front and back. And in this case right here, we have enough hydrogen, or we'll be able to find hydrogen that now anti-coplanar to this bromine right here on this carbon. And that's where the reaction would occur. So in this case right here, there is regioselectivity in this E2 reaction, where it can only pick up either one of this hydrogen right here, does not matter which one. And we'll be producing this product. And now let's try I. So this is the E2. So in I, so this is very much similar to the example in H, except there's some differences. So here in this case right here, we do have a hydrogen pointing on the back at this beta carbon. So in this case right here, the base will be able to come in and pick this up to now produce the other alkene. And again, we will then see that we can form substitution SN2 product and E2 product as well. So now let's draw the SN2 product first. The SN2 products is when the carbon come in to attack the alpha carbon directly, and now we'll be able to have this product right here. So that would then be the SN2 product. As for the E2 product, now we would then be able to, again, it can happen where at this hydrogen right here, and this electron is donated in, kick off the leaving group, so we'll be able to make this alkene product right here. So that will be one of the product. Now we can also produce the other alkene product, where the base come in to pick up the hydrogen from the other beta carbon, and in this case right here, we'll be making this product. So these are the product of E2 reaction, and this will be the SN2 product.